Okay, believe it or not, this is going to work. I am not sure about our nation's nuclear secrets, but I can tell you that Washington University is protected. It is just completely safe, and it is impossible for professors to figure out. So this is not the classroom that I normally use, and they've changed it a little bit since the last time I was in here. In fact, they kind of change everything. But so thank you for all for bearing with me. Thank you all for coming today. As you probably realize, we made a decision to not have these lectures as hybrid lectures, which can be viewed on Zoom and can at the same time be viewed by a live audience. You know, I know that that's a difficult decision for us to make, and it's hard for some people, but I am recording today, and that will be posted to the department's Zoom channel. And what you saw me fumble around with was me navigating the university's various security systems and getting logged into the university's network, Zoom, and everything. But everything seems to be working just fine. The reason why we're not embracing a hybrid modality is simply because with one guy doing all the things, it's just hard. Last spring, my wife informed me at the end of one of these lectures that, you know, for the entire time, the camera had been focused on an unfortunate part of my anatomy. And, you know, that's just an indication of the kind of things that can go wrong. When we were during the height of the COVID pandemic, for a large lecture situation like this, we typically had 2 or 3 people, you know, one person giving the lecture and the other 2 monitoring the systems and the students. You have a microphone? I think I can dig one up, but it'd probably take me so long. How about if I just talk a little louder? Is that okay? Good idea. All right. All right. So anyway, this should be recorded and it should be up after maybe a week or so on the university's Department of Physics web channel. So what I'm going to talk about today is I'm going to talk about Oppenheimer's pre-war research. That is, the bulk of his scientific research was carried out prior to World War II, and how that is tied to the rise of American quantum physics, not quantum physics in general, but American quantum physics. And I'm going to try and answer 2 questions. One is a question that people sometimes ask, which is, why didn't Oppenheimer ever win a Nobel Prize? And the second question is, what made Oppenheimer and Compton, in my opinion, the 2 essential people on the Manhattan Project, the 2 absolutely irreplaceable members of the scientific team that worked on the creation of the first nuclear devices. And I think, you know, that by the time I get to the end, you'll understand both of these pretty well. In order to explain what's going on, I need to tell you a little bit about the history of quantum mechanics and the personalities that sort of populate that history. So we're going to go through 4 generations of quantum physics prior that, you know, were active before the war. Generation is a little misleading. If I had to say, I'd say that the people in the different generations are separated by about 10 years. Now in scientific research, maybe a generation is 6 months. I don't know. We're like fruit flies. Oh, there we go. The first generation is really the pioneers of quantum theory. Planck, of course, with his discovery of black body radiation, in some sense, the last classical physicist. He didn't really quite grasp the implications of what he did. The person who first really grasped what was going on was Einstein, whose work on the photoelectric effect was what earned him a Nobel Prize, and his work on phonons. This is really interesting stuff because he said it's not just photons of light that are like particles, but there are other quantized vibrations like phonons, which are the quantum vibrations of a solid. And he said it's a general phenomenon. And then that was followed by Bohr, who said, well, quantum physics applies to the electrons of the atom. It explains their spectral properties. And then de Broglie, a little bit later, who worked on the wave-like properties of particles. And so this is, of course, Einstein himself, and this is Tom Conti, who played Einstein in the Oppenheimer movie. And of course, he's a Nobel laureate, as are almost all of these people I'm going to talk about. The second generation was the codification of quantum physics and turning it from something of an art, where you're sort of like reaching to different parts of physics, classical physics, and what you know about the quantum world and cobbling something together, like an explorer in the wilderness. In the second generation, Heisenberg and Schrödinger came up with a precise formulation of what quantum mechanics was, that meant that if you understood the equations, that pretty much you could tackle any quantum problem that you wanted to. So this was a big advance, for which, of course, they received the Nobel Prize. Born, who we'll talk about a little bit later more, came up with what's now known as the Born interpretation of the wave function, which says that the fundamental thing in quantum mechanics is not physical. It's a probability wave function. It's not like an electric field or, with the location of a particle. It's really a probability amplitude. And this is part of the foundation of quantum mechanics as we understand it today. And then sort of completing the second generation, Dirac came up with the Dirac equation, which we can think of the Schrödinger equation as kind of the non-relativistic theory of quantum physics. And Dirac's equation is the relativistic theory of the electron. And so that represented an extension of quantum mechanics into relativity. And here you see Niels Bohr as he appeared in real life, playing himself. And here we see an actor playing him in the movie. The directors and producers clearly went to a bit of trouble to sort of get people who could convincingly play the role. These are, I'm sure you realize that a lot of these gentlemen are very good actors, very well known, and some resemblance to the people they played. So in the third generation, we had the foundations of quantum physics, and we began the application of quantum ideas to more problems. So Enrico Fermi, the man who created the first atomic reactor under the squash courts of Chicago, invented a lot of physics, probably the last great physicist to be both a theorist and an experimentalist. And his name is attached to a lot of applications of quantum physics, including, for example, Fermi statistics, the theory of the weak interactions. He coined the term neutrinos, a small neutron in Italian, il neutrino. And of course, he also received the Nobel Prize. E.O. Lawrence, who is Oppenheimer's best friend in life and in the movie, the inventor of the cyclotron, for which he received the Nobel Prize. Hans Bethe, also in the movie, who received the Nobel Prize for his work on stellar nucleosynthesis, which relies on quantum physics in an intrinsic way. And that basically takes us up to the beginning of World War II, which of course, as you know, did not begin with Pearl Harbor, but had deep roots in the 30s until the US entry into the war. It was not until after the war when the people who had been involved in the war effort, like Julian Schwinger, who worked on radar, and Richard Feynman, who was at Los Alamos, were able to go beyond what the previous three generations had done and come up with a synthesis of quantum physics and many-body physics that was completely satisfactory. And this culminated in Schwinger and Feynman's work on quantum electrodynamics, about which I'll say a little bit more later. And here's Feynman in life and the actor who played him. He's the guy that you could hear playing the bongo drums after the Trinity test in the movie. Okay, so you'll notice that I've mentioned some of these, all these great men, and they are great men. All Nobel Prize winners that I've shown you pictures of. I think all of the people, yeah, all these guys are Nobel laureates. And I didn't include Oppenheimer. So where does Oppenheimer fit into all of this? Well, so he's a very smart guy, came from a wealthy New York family. His father was a businessman. He got a BA in chemistry from Harvard in 1925. He graduated summa cum laude in 3 years. And for part of that third year, he wasn't even in Cambridge, Massachusetts. He was actually in Cambridge, England in 1924. And that's shown in the movie as he's visiting the Cavendish lab at the University of Cambridge. So summa cum laude in 3 years at Harvard is pretty good, And then after traveling around a bit in Europe, he ended up in Göttingen, okay? And in 1927, remember this is only 3 years after 2 years really after his technical graduation from Harvard, he got his PhD under Max Born. Remember, Born is the guy who came up with the Born interpretation of quantum mechanics, of the quantum mechanical wave function. And that was where he started to meet all these then young European physicists, Werner Heisenberg, Wolfgang Pauli, Paul Dirac, Enrico Fermi, Jordan Teller, all these guys that, were giants of quantum physics. And then after that, he returned to the United States with a National Research Council fellowship at Harvard and Caltech. He split his time. And so that was like a super postdoc position, okay? And then he was splitting his time between Harvard and Caltech, and they were so eager to hire him at UC Berkeley that they hired him as an associate professor, okay? Not an assistant professor. They hired him as an associate professor in 1929, and he became a full professor there in 1936. And that's pretty much where he was until he joined the Manhattan Project in 1942. And then he was appointed director of Los Alamos in 1943, although he had long been functioning in that role, as director since 1942. And really this time from, about 1925 to 1942 is really his active phase of scientific research. So relatively short, about 17 years. So, what did he do? Well, he did a lot of different things. And there were certain themes in what he did, which I'll talk about, but this is basically the highlights, except for his work on astrophysical processes, which I'm not going to talk about today, but in the Lee Sabatka, who's in the audience somewhere, there's Lee, is going to talk about the war years, mostly, and then in a week after that, and then the week after that, the week before Thanksgiving, Professor Mark Alford and Mike Novak are going to talk about Oppenheimer's contributions to astrophysics, as well as sort of the culture he engendered at Los Alamos. It's pretty interesting, but I'm not going to talk about that today. So, his initial work was on the theory of molecular band structure, and I'll talk about what that is. And as a sort of a theoretical development or extension or improvement in the treatments of molecular band theory, he and his thesis advisor came up with what is now known as the Born-Oppenheimer approximation. And that is a very beautiful piece of physics, a very powerful idea. It's still his most cited work, okay? And then he worked on the theory of tunneling, and I'll explain what that is. He worked on the infinities in the electron's self-energy, a very difficult topic, and also predictions of the existence of a positron, also not quite as difficult, but pretty difficult. These are the kinds of issues that were only resolved after World War II, okay? So Feynman, Schwinger, Tominaga, all received the Nobel Prize for their work on these kinds of issues. And really, it was Freeman Dyson, though, who showed that Schwinger had a set of techniques, Feynman had a set of techniques, the Feynman diagram. And it was Dyson who actually showed, after their work was published, that in fact the two ways of looking at things, the two formalisms, were equivalent. Okay, so this is work that is a bit of prophecy or clairvoyance, looking into the future, as it were. And then again, along the same line, Hall, who was a graduate student of Oppenheimer, predicted something called the Lamb shift, showing that Dirac was in fact wrong. Dirac was not often wrong. And that's also belongs to this set of sort of really very difficult and sophisticated topics that he worked on. And then finally, I'll talk just a little bit about the Oppenheimer-Phillips process. This is work that Oppenheimer did with his graduate student, Melba Phillips. Okay, so that's where we're headed. Now, I'm going to tell you a little bit more than you want to know, maybe, about the rotational and vibrational structure of the spectra of molecules. Now, I think a lot of you know that there are electronic transitions in atoms that give rise to spectral lines, okay? These are why we're able to find out things about objects in space, because we can look at their spectra. And these kinds of electronic excitations and their associated spectral lines are in the visible and in the ultraviolet part of the electromagnetic spectrum. Molecular spectra are different. They're much lower in energy, and that means they're much lower in frequency. And that means that the rotational part is in the infrared. And then there is a vibrational component, which is actually a little microwave part of the spectrum splitting, lower in frequency still. And what I mean by this is, let me consider the simplest possible molecule, okay? A molecule with two atoms, like nitrogen in the air we breathe into, or O2, or H2, or hydrogen chloride, okay? You know, which is actually hydrochloric acid when it's dissolved in water, okay? So you've got two atoms, and to a first approximation, you can think of two masses held together by a rigid, invisible rod. And what can these molecules do? Well, they can spin, they can rotate. And when they rotate, they have angular momentum. It's not the electrons of the system that are doing anything. It's the whole system, the nucleus, the electrons, the whole thing is rotating, it's tumbling. And that rotation is quantized. Bohr was the first one to really explain why this is. Here's the quantization condition that says the energy is proportional to the angular momentum squared divided by the 2 times the moment of inertia. And Bohr says, well, actually, he would say it was L squared, but the correct answer we now know is LL plus 1, H bar squared over 2I. And where L is an integer, this is quantization at work. And the appearance of H bar, Planck's constant, tells us, yep, this is quantum, okay? So it's got these energy levels, and it can go, you know, it can go kind of, I'm not going anywhere. I dare you to make me move. And then you kick it a little with something, and then it says, okay, I'll move this much. And you kick it again, and it says, okay, I'll move a little more. But it jumps, right? It's quantum, so it goes, the energies go in discrete jumps. And the kind of weird thing about this is that there's something else going on in the molecule. Not only is it doing this tumbling thing, right? But the chemical bond that is given originates in the sharing of the electrons between the two nuclei in a diatomic molecule. That is also fluctuating. It's going back and forth. So it's not only rotating, but it's also vibrating, okay? And these vibrations are also quantized, okay? And so you have a very complicated system that can rotate at certain energies, at certain speeds, and can vibrate at certain speeds. And when you put all this together, what you find out is that you get a very, very interesting and sophisticated pattern. Because of the way that photons work, they carry angular momentum themselves, there's a missing line in the middle of this spectrum, which is actually the center of the whole thing, which corresponds to zero rotation. And then you see all these different transitions all in the infrared. This is for hydrogen chloride, by the way. And, you know, you get all these different energy levels, and they represent transitions between the different energy levels of the system. And you can use these spectra to identify what the molecules are. Okay, this is, my dad led an analytical chemistry group at Monsanto for years, and this was part of their bread and butter, okay? Infrared spectroscopy of various kinds, okay? So if you see a characteristic pattern like this at a known characteristic middle frequency, then you could tell that, you know, there was HCl in your sample, okay? So this was the earliest work that, that Oppenheimer did. And that led to a theoretical understanding of how this worked called the Born-Oppenheimer approximation. Famous approximation, and it comes directly out of the fact that the things I told you about molecules just now are a lie. Because I told you that you could think of the molecules as being two masses connected by a stick, and that's not quite right. And then I told you that actually there was some vibration back and forth in the chemical bond. And that's true, but it's not really fundamental. Neither of these things are really fundamental. Remember, what's actually happening is that the two atoms are bound together because they're sharing electrons. That's what the chemical bond is. And so, you know, when you have the molecule vibrating, what's happening is that the electrons that make up the chemical bond are changing their conformation, right? And it's changing the energy in subtle ways because these charged objects, the electrons, are moving in response to the motion of the atoms, which are positively charged. Okay? And so what Born and Oppenheimer said was, they said, well, look, there are actually two different sets of degree of freedom in this problem. There's the electrons that make up the chemical bond, and there are the atoms, and the atoms are much, much heavier than the electrons, okay? If you take a look at H2, which is, you know, the simplest diatomic molecule, the mass of the nucleus of the, you know, typical hydrogen atom is just a single proton. And the mass of that proton is about 2,000 times the mass of the electron. And what Born and Oppenheimer realized very cleverly was that although all of this is a quantum system, there are fast modes, the electrons, because they're light and speedy little guys, and there are slow modes. In the hydrogen, it would be the proton. In general, it would be the atom itself. And you can neglect the motion of the atoms when you're considering how the electrons in the chemical bond are moving. And so what you do is you say, okay, I'm going to fix the distance apart between the atoms, and then I'm going to solve for the behavior of the electrons using the Schrödinger equation. And then once I've got that, I will get an effective potential energy, which describes the interaction between the nuclei, which includes the effect of the electrons. So you've got these guys, these atoms, right? And they interact with each other via Coulomb potential. It's quantum physics. But there's also an effective interaction, which is mediated by the electron cloud between them. And by making this Born-Oppenheimer approximation, I could simplify the problem enormously and make it much easier not only to understand qualitatively the physics, but actually quantitatively calculate. So it's a famous approximation, and it's a paradigm for the way we think about physics. In a lot of problems in physics, we like to separate the scales. Okay, when you're doing cosmology, you're usually not thinking about quarks. Sometimes you are, but in terms of the large-scale evolution of the universe, we're usually just thinking about gravity and the initial conditions of the universe, you know. And so, you know, when you're driving your car, you're not thinking about the quantum processes that are going on, you know. So there's this natural separation of scales, where we're able to think at different sizes, different energy scales. And so this is a very powerful idea. And in some sense, I think the Born-Oppenheimer approximation is really a paradigmatic example of how that works. Okay. Now, a little more. He also worked on something called quantum tunneling. And this is, remember that this is the era in which people are learning to apply quantum physics. you know, Heisenberg and Schrödinger, they said, okay, this is how you do it, but they didn't solve all the problems that could be attacked by quantum physics. No one person could. And so people sort of said, what are the problems that we can now attack now that we've got this formalism? And quantum tunneling is one of them. And it's really, in some sense, a really good example of how weird quantum physics is, okay? And it's a simple enough idea. Okay, how many of you know someone who has accidentally run into like another car or a barrier, you know, a highway barrier? If you drive around campus, you'll see them everywhere. You know, you don't have to admit to your own personal. I'm certainly not going to admit to mine, but you probably know somebody. You know, well, you know, in our macroscopic world, if there is a potential barrier, you know, like a door or something, you know, and a classical object hits the door, you know, either the door breaks, which is not the typical behavior, or you don't go through it, okay? So that is classical physics, macroscopic physics, physics at our size and scale, but it's not what happens in the micro world. So if you have a particle, which is, say, coming into this potential, this is the simplest kind of potential we can have. It's a square potential. So over here, the potential 0, it jumps up to V0, and it goes back down to 0 over here. So it's a barrier. And if you come in like this way, then if it were you and I, we would hit the door and we would bounce off. And that would be 100% reflection. But that's not what happens in quantum mechanics. What happens in quantum mechanics is that if you come in and you don't have enough energy to get over the barrier, you know, you're not up here with lots of energy to go over it. You know, in quantum mechanics, there is a small probability that you can go through the barrier, even though you don't have enough energy to do so. And this is what we call tunneling, okay? And if you look at it, it's illustrated here. You've got this incoming particle. It hits this block, and you get some reflection. And then there's something going on inside this block here. And then you get some wave that's transmitted, and then you get some wave that's reflected, okay? And so this is a graph of the transmission probability as a function of the energy over V0. So if you're below 1 here, you don't have enough energy classically to get through, but quantum mechanically, you do. Right? There's a small probability of going through the barrier. And this is what Oppenheimer worked on. What I'm describing to you is the way that I would teach this in our sophomore quantum physics class. That is not what Oppenheimer did. Remember, they didn't quite really know what they were doing. He solved actually a much harder problem, which was the 3-dimensional problem. This is a 1-dimensional problem, right? There's a moving along a line. And he didn't solve it in a simple way. He solved it probably the most complicated way you can imagine, which is probably typical of the way he approached problems. He loved to use hard mathematics. He loved to get himself in so much trouble that you didn't see how he was going to get himself out. And then he did, right? But he did calculate the 3D transmission probability, which is the analog of this for a 3-dimensional object. Imagine an atom and you send like an X-ray and you want to know if the X-ray will make it through, something like that. And he did obtain the correct leading factor. And I got to say, I've looked at the paper and it would probably take me a very long time to get through it. We don't solve these problems the way he did it. But of course, he was a pioneer, right? And so he's doing all this work on very important fundamental issues, and he's making real contributions. And now we come to him really tackling some of the most difficult problems that arose out of quantum physics before the war, the problems that were not really fully resolved until after the war, okay? And one of these is the infinities in the electron's self-energy. So the electron appears to be a point particle. You know, we can debate what the definition of a point particle is, but, you know, it appears to be a point particle. It doesn't have internal structure. It's not a ball. It's a point, okay? And if we want to understand how that works, we can think of the electron as a uniformly charged sphere of radius A. You know, the electron has some charge, so you imagine putting it together. So you bring in all the charges from infinity and you put it together and say, how much energy is in the electron? Because it's got a positive charge and positive charges repel. So the positive charge has to kind of repel itself. So it takes energy to make an electron. I mean, that's the naive argument. And if you calculate that energy classically, it's this thing here. This is, you know, 1/4 pi epsilon naught is because we're using international units. The 3/5 is because of the way we assembled it. It's a uniformly charged sphere. And the q²/A is where the real physics is. It's the charge divided by the radius, charge squared divided by the radius. And the important thing is that no matter how you calculate this, no matter how you model an electron classically, you find out that if you take this A to 0, the energy blows up. It takes an infinite amount of energy to assemble a point particle with a given amount of charge. And what Oppenheimer showed is that this is also a problem in quantum theory. I mean, you can say, okay, classical physics is not right for electrons. But what Oppenheimer did was he showed that no, the problem actually persists in quantum theory. It takes a different, more sophisticated form. In modern language, what we would say is that there's this Feynman diagram, which represents an electron, and it emits a photon, and then it reabsorbs the photon. This is the self-interaction, the electron interacting with itself. And if you calculate this diagram, you find out that it's divergent, it's infinity, okay? And Oppenheimer didn't solve the problem, but he showed that it was a real problem, okay? It showed that you couldn't just sweep it under the rug. And this problem was only solved by renormalization, which is a technique of quantum field theory. It was something that was worked out by Schwinger and Feynman after World War II in the case of quantum electrodynamics. And, you know, now it's sort of a rite of passage for, you know, like second and third year graduate students. If you're crazy enough to understand how renormalization works, how you can sweep the infinities away, then you're crazy enough to do theoretical physics. But it's hard. It's really hard to understand. Okay. So, you know, he understood that this was a real problem. And then at the same time, he got interested in the problems, other problems of what we would now call relativistic quantum mechanics. And he said, okay, Dirac has this Dirac equation, which is the relativistic analog of the Schrödinger equation. And it makes all these great predictions, which are all true. It predicts the existence of the positron, the antiparticle of the electron. It predicts that the electron has spin a half. And it predicts, this is a little subtle, but the G factor of the electron is 2. If you ask how a magnetic field couples to the electron, it couples to its angular momentum classically. And so you'd say, well, I've got the angular momentum because it's going around the atom, and I've also got some spin, and that gives angular momentum too. So it should couple to the total angular momentum, which is L plus S. And the answer is no, that's wrong. There's a fudge factor. It's actually L plus 2S. The 2 is the fudge factor. That's what we call the G factor, the gyromagnetic factor. And it was kind of this embarrassing thing, like, why is that 2? I don't know, And so, Dirac's theory had these 3 classic great predictions that, convinced everybody that he was right, and they gave him a Nobel Prize pretty quickly. But there was a subtlety here. Many scientists thought that maybe the proton was the antiparticle of the electron, because you see electrons, the Dirac equation predicts antiparticles, oppositely charged particles that you would see. And so people say, well, we see electrons, we see protons. Protons has positive charge. Maybe that's the antiparticle of the electron. And Oppenheimer said, no, that can't be right. Okay, because if that were right, then the hydrogen atom would be the antiparticle, the proton in the hydrogen atom would be the antiparticle of the electron, and hydrogen atoms would be unstable. The particle and the antiparticle would annihilate each other, and all the hydrogen in the universe would disappear, and we would disappear with it. That would be bad, or something. It would definitely lead to a different place than we are. He said this can't make sense. He said no, the proton cannot be the antiparticle of the electron. It has to be something with the same mass. And in 1932, just 2 years after his work, Carl Anderson did discover the positron. And then once that was done, Dirac received the Nobel Prize in 33, and then Anderson in 36, and everybody was happy. So you can see, that Oppenheimer is enormously influential here, even if he isn't completely resolving the scientific issue. Okay, another one, the Lamb shift. Again, this is a really small effect that you can only understand with relativistic quantum mechanics, so quantum mechanics, relativity, and there's something else you need many body physics. So this is what places it in the realm of quantum field theory. Quantum field theory is the many body theory of relativistic quantum mechanics. And Dirac had said, well, if you look at the Bohr theory says that the hydrogen atom has these energy levels. There's the ground state, then there's the first excited state. These are the 2s and 2p levels in the Bohr theory, and they're degenerate. And then Dirac says, well, actually they're shifted in the Dirac equation. And so, there's actually a subtle effect here. There's some splitting between the 2p3 halves and the 2p1 half level, which you can see. And he said, but the 2p1 half and the 2s1 half levels, they're the same. That's what the Dirac equation predicts. But Oppenheimer and his student, Harvey Hall, looked at the data and they said, well, looking at the data, I think there is a splitting there. We think that Dirac is wrong. And it turns out they were completely right. This reason there's a splitting is because when you look at the positively charged proton in the hydrogen atom, there are virtual pairs of positrons and electrons that appear in the vacuum and give rise to an effect called vacuum polarization. It changes in a very, very, very small way the potential that the actual electron going around the proton sees. And that little tiny shift is the Lamb shift. And in 1947, after the war, Hans Bethe calculated the splitting in a way that was not completely free of problems, but looked good. And then Oppenheimer's former student, Willis Lamb, notice it's Oppenheimer's former student doing this work, measured it experimentally, and Lamb won the Nobel Prize subsequently for that understanding of the splitting. So, you can see, so Lamb was Oppenheimer's theory student after he had done the work with Hall, and after he had done this work in 1931. And so, of course, you're always aware of the kind of work that your thesis advisor does, right? So Lamb was unusual because he switched from theory with what he did with Oppenheimer to experiment. And then he did this very precise experiment to measure the Lamb shift, okay? And so, you know, okay, I think you're getting the picture, right? It's like Oppenheimer is some guy, you know, everybody but him is getting dates with all the pretty girls, right? Everybody's getting Nobel Prizes. My friends are getting Nobel Prizes. My students are getting Nobel Prizes. But, you know, okay, that was how it worked out. So I'm just going to finish up with a very brief description of the Oppenheimer-Phillips nuclear process. This is work he did with Melba Phillips in 1935. And again, it's a really interesting thing. It's a little subtle. If you have a deuteron, this is the nucleus of heavy water. It's a proton, like a normal hydrogen atom, but there's also a neutron present in the nucleus. So this is a deuteron part, and this is, if you make hydrogen out of it, you get deuterium, okay? And it changes one isotope into a heavier one by colliding a deuteron with another element. So what happens is the neutron and the proton are coming in together, and the neutron only has a strong nuclear force affecting it. And so it likes to get close to this other nucleus, okay? The proton, on the other hand, also has a strong nuclear force, and the strong nuclear force says, oh yeah, get close to this other set of nucleons. But the Coulomb charge of the nucleus and the Coulomb charge, the electric charge of the proton says, no, we're both positive, we're repelled. And so the neutron is more welcome than the proton to sort of join the gang. And so this is kind of strip reaction is really interesting and pretty ubiquitous. And so what happens is the neutron stays here with carbon-12, it bumps it up to carbon-13 with the addition of a neutron, and the proton is left free to move off. So pretty interesting. I just thought I'd say a few words about Melba Phillips. I met her here years ago, very interesting woman. At the time I met her, she was not young. You know, she was one of Oppenheimer's first graduate students. She was a professor at Brooklyn College, and she did research part-time at Columbia University throughout the, pre-war, and then past the end of the war until 1952. And then as part of the whole McCarthy era thing, she was called before the McCarran Commission. This is one of these special purpose commissions investigating communists. And she invoked her Fifth Amendment rights, and then she lost her position and she was unemployed. And while she was unemployed, she supported herself in part off of her savings, but also by writing textbooks. And she wrote a book, famous graduate level textbook on electricity and magnetism called Classical Electricity and Magnetism with Wolfgang Panofsky, who is also a very famous physicist. Now, the interesting thing is that after that, she came to Washington University, which was a bit of a haven for refugees from Congress. Washington University was, offered positions to a number of physicists. Ed Condon was one, who for various reasons drew the attention of Congress because the administration here was very supportive of academic freedom. And then she went from here to the University of Chicago, and then she became a professor emerita at Chicago. But she kept on. She was a very, very well-known physics educator. in addition to her contributions to science. And throughout her life, she was a very strong advocate for physics teaching, made a lot of contributions there. It's pretty interesting. Now, as I said at the beginning, I'm not going to talk about Oppenheimer's work in astrophysics. That'll be in 2 weeks and 3 weeks from now. But I'll just mention that he did some work with Robert Server, also in the movie, okay, who on white dwarf stars. His work on Volkoff on the mass limits for neutron stars. His work with Snyder on the existence of what we now call black holes. But aside from those astrophysical papers, I've really sort of covered the major works that he did prior to World War II. After World War II, he only published 5 papers. Of course, at that time, for a lot of that time, he was the director of the Institute for Advanced Studies. He was very involved in the administration. Whole other interesting chapter in his life. And of course, then came the security hearings, which if you saw the movie, you saw how Louis Strauss basically persecuted him for personal reasons. So let me try to answer the 2 questions that I posed at the beginning. So I don't know if you can read this cartoon. This is one of these famous New Yorker cartoons. The woman is entertaining in their New York apartment, and she turns to her husband and says, "It was just that one time that you won the Nobel Prize, wasn't it, dear?" Yeah. I mean, sometimes it's kind of like that, University administrations are like, "Well, what have you done for us lately?" There are a few people, very exceptional people, who have won more than one Nobel Prize. But this kind of, I think, sums up, in the words of, people who knew Oppenheimer, his standing in the community. Hans Bethe said his most important ingredient he brought was his exquisite taste in problems. He knew what were the important problems as shown by his choice of subjects. He lived with the problems, he struggled for a solution, and he communicated his concern to his research group, right? So, you can see he was working on important things. He maybe didn't get the complete solution for some of these important problems, but he was identifying them and making important contributions. Murray Gell-Mann, who knew Oppenheimer after World War II, another Nobel laureate, he didn't have Sitzfleisch, German word that means, sometimes that's used in chess, you sit in a chair and you just sit. It's the capacity to sit in your chair and do stuff. He never wrote a long paper or did a long calculation, anything of that kind, but he inspired other people to do things, and his influence was fantastic. And this is, Victor Weisskopf was one of the youngest people, along with Feynman at Los Alamos. I knew him when he was a grand old man and I was an undergraduate. Oppenheimer directed the studies, theoretical and experimental in the real sense of the words. His uncanny speed in grasping the main points of any subject was a decisive factor, for he could acquaint himself with the essential details of every part of the work. So what he's saying is that during the Manhattan Project, Oppenheimer had this tremendous overview of all the enormous problems, okay? For example, one small detail that you don't actually hear much about during the movie is the use of an explosive lens. This is the design of the Trinity test. It's an imploding conventional explosion that forces the plutonium together to cause an explosion. This was an enormous technical barrier to making a plutonium device. And, Oppenheimer kept track of 1,000 things. and he was there all the time. And, you know, in the movie, you see how people are congratulating him. And, you know, they all worked on it, but they see it as his triumph, because he was the guy who directed everything. And I think in some sense, you know, you've seen kind of why he never won a Nobel Prize quite, but he was clearly in the top rank of physicists. In fact, I would argue that he and Compton were the essential components of the Manhattan Project, you know, because what were they? They were American physicists who had received European training and were well respected by their European colleagues. Remember how many people escaped from Europe and came to Los Alamos to work on the bomb from Europe? These were all brilliant men. They weren't going to work for somebody who was an idiot. They respected Oppenheimer and they respected Compton, you know, and their confidence and their trust were well placed. But from a US government point of view, you're not going to take somebody who just stepped off the boat, right? A refugee from Europe, no matter how prominent they are, and put that person in charge of a $1 billion research program to defeat the Axis. No. They had to have somebody like Compton and somebody like Oppenheimer. Compton did a tremendous amount of work throughout the Manhattan Project to provide the isotopes that were necessary for the creation of the atomic devices. Whereas, you know, Oppenheimer, as director of Los Alamos, you know, was the person who oversaw the actual design of the bomb. And in fact, it was Compton who suggested him for the job, who put him forward for that job. Okay. So, you know, I hope you've enjoyed this. And, you know, I hope this has given you a little bit of insight into the background of the movie, which I thought was a very good movie. And maybe a little insight into quantum physics and, you know, the history of it all. So thank you all for coming. Thank you all for your patience. And I'd be happy to answer any questions you have. Yes, ma'am, in the back. Oh, I don't think she needs defense, but go ahead.
I never heard her name until I went to the University of Chicago, where she taught an introductory physics course. She was from St. Louis, grew up here, and probably was unemployed, I'm not sure, for a while because of her gender. And
Actually, no.
It's easy for her to get hired here eventually because she was a local girl.
She was unemployed because she was labeled as a communist.
Because what?
She was labeled as a communist. The fact that she was employed at Brooklyn College and had a part-time gig at Columbia, that I agree. That's probably because she was a woman.
But being a female probably didn't give her much help. And she had a very distinguished family here. Her brother was a pediatrician. I mean, it goes on and on.
Yes. And that is one of the reasons why I paid particular attention to her, is because of the connection with Washington University. And because she was very true. And probably several different ways.
Well, I worked in the physics department in the late 60s. We never heard her name.
I heard I was here.
Well, I think you know, people did. I mean, I'll be honest with you, in terms of her research contributions, she was not in Chomsky's class. You know, very, very well physicist. Whether that's because of lack of opportunities or I can't say. I can only tell you the history as it happened. I can look at her research record. I can say that her contributions to physics education were enormous and lifelong, for sure. And, you know, the Oppenheimer-Phillips process is very, very well known and essential. You know, it's not a bad legacy. Not really a bad legacy. Yes, sir.
Did Compton work with Oppenheimer? I didn't get it mentioned in Compton.
You
Oppenheimer.
mean, oh, did they do research
Yeah.
together? No. Compton was an experimentalist. He always was an experimentalist. Oppenheimer did collaborate as a theorist with E.O. Lawrence, Ernest Lawrence, who's in the movie. Basically, Lawrence was essentially Oppenheimer's best friend. They were sort of right next door. Oppenheimer, Lawrence was the guy who invented the cyclotron. But yeah, I mean, this was a small community of elite scientists, and they all knew each other, right? You know, Compton and Oppenheimer were not all the great men. But they didn't necessarily.
Back a few slides ago on that Born ship, did the Born ship actually change the energy levels of the 2s and 2p energy level of all?
I'm sorry, the Lamb ship?
Of the Lamb ship, I'm sorry, not the Born ship, the Lamb ship.
Yeah, so what happens is to lowest order, these vacuum polarization effects induce a slight shift in the Coulomb potential. It's called the Uhling potential. It's essentially a kick at the origin.
So it's really not
It
degenerate,
changes the energy of the 2s level.
but it's not purely degenerate then, is it?
It's not purely degenerate, right? Yeah, that's right. So the slide I showed did not show the Lamb ship. Although to be fair, it's so small that it's really a tremendously small effect. It is, or it was at the time, one of the most precise ways to actually determine the strength of the electron's charge, what we call the fine structure constant. Because you could measure this very small shift in energy very precisely. You had a very precise theoretical prediction, and so it was a very precise measurement that related theory and experiment and beautiful that. And it's still true that QED is the most successful theory we have. Most of our most precise ways of defining physical constants come from QED one way or the other.
Did Oppenheimer have a gap in his employment due to the problems? Or I mean, what were the consequences? It doesn't appear in the movie.
Oh, yeah. So by the time that all happened, Oppenheimer had already been director of the Institute for Advanced Studies, where Einstein was in Princeton for a long time. And I think the real penalty he paid was that here was a man who had lived for decades, really, with America's nuclear secrets, and was this is a guy who was on the cover of Time magazine. He was the most famous scientist in the world, and now he's, it's like going from like Taylor Swift dating Travis Kelce to some schlub physics professor at Washington University. It's like, it's a real fall from grace.
And probably also affected his trying to influence what happened to the bomb and so on. Political influence.
Yeah, the history of his attitude toward the hydrogen bomb and his interactions with Edward Teller and Edward Teller as a person, that's another fascinating chapter. Oppenheimer was liked and respected in spite of the fact that he was kind of a womanizer. Teller was more respected than liked, I think, by a lot of people. you know, he had a difficult personality, but it's, you know, it's really hard to figure out all the personal interactions at this distance. I mean, I kind of hear things, you know, so, you know, my academic lineage is such that I hear stories about Feynman and Schwinger and people before them, you know, and they come down to me like, you know, like people hearing the Iliad and the Odyssey recited 500 years after it was first recited by Homer, but before it was written down, you know, so it's sort of this oral thing. Is there a question over there?
On the Oppenheimer-Phillips effect, to the unprepared mind, you might think it would come out just the opposite. The strong interactions for a proton and a neutron are about the same. The proton is repelled, slowed, and therefore would get captured more easily, and the neutron would just fly through.
Oh, you're
Since it
thinking,
suffers no diminishment in velocity. So it must indeed be a more concentrated, more difficult theory to.
Well, you know, I was thinking about that, and you know, Lee, there must be some non-zero cross section for just pure deuteron capture, right?
Well, there's both deuteron capture, there's NP, and there's, I'm sorry, there's DP and NP in it. But this is you mostly get the DP, in other words, the neutron capture, at low energy. And the deuteron stays bound until the moment, essentially the moment of capture, and is polarized with the proton away. And so it doesn't, the cross sections even out at higher energy, but at low energy, you have the Oppenheimer-Phillips, and the neutron gets captured, and so you have DP going out. And its value is that it's very hard to do neutron experiments. To shoot a neutron, I mean, you do them, but what is the energy? But if you shoot a deuteron and a proton escapes, you've effectively done the equivalent of a neutron capture. And so its great value is a surrogate for doing neutron capture experiments. But then all your exercise, the whole exercise gets morphed into how it is really different from a great neutron capture. Actually, that's still a lot of theory that goes on today.
Yeah, so the proton kind of functions like a electric handle because it's got a positive electric charge, and it's easy to manipulate.
On Melba Phillips is teaching here. I don't think you mentioned the special program.
She was associate director, I think, of the teaching staff.
It was right after Sputnik. Everyone was trying to beef up high school teaching of science, and she came here to head that program. Ed Condon was a great friend of hers, and politically.
They had something in common. They both dumped on like. Yeah, I didn't, and I have to say, you know, I could stand up here and I could talk literally for hours about Los Alamos and about the history of nuclear weapons. I could talk about the history of quantum mechanics. You know, if you've seen this movie, The Longest Day, about D-Day, right? Well, really long movie, great movie. And pretty historically accurate, like the Oppenheimer. And you know, D-Day is just sort of endlessly fascinating because there are all these vivid personalities in these stories. Well, the Manhattan Project is exactly like that, except instead of getting soldiers, you've got physicists. But still, there's all this, there's all these vivid personalities. I haven't told you, for example, about all the, women that Oppenheimer interacted with. And I don't think we've got enough time. You know, and things like that. Yes, sir.
Not technical question, but who's on the horse?
Okay, I don't know, but, you know, I feel a certain kinship with J. Robert Oppenheimer. So this is that's a mule, of course, and the mule is walking down. I guess this is the Bright Angel Trail from the south rim of the Grand Canyon. And I don't know if you've ever done this, but the mules have right of way. So, you know, we are sort of up against the wall on the other side of the trail, and the mules are trained to walk near the edge of the trail. And this is, I think, the trail leader, you know, the paid guy who's leading the people who are taking the mules down to the bottom. And it was just such a striking picture that, you know, I just decided to show it. And, you know, I don't think I would ever really like to live permanently in the Southwest, but Oppenheimer loved it. You know?
Was it young Mike Ogle?
No, 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 the closest I've come is my mother telling me I'm stubborn as a mule. Yeah,
Even the mule in the picture.
but yes. A phone. Oh, okay. So in a solid state system, again, we're back to the system of atoms bound together, this time into a big solid. And you can think of the bonds between the individual atoms in the solid as being connected by springs, right? And so classically, what you've got is, you know, a thing that can vibrate. So if you take a solid, like a solid crystal, and, you know, like a railroad track, they always do this in the Westerns, right? You can always hear the train coming through the railroad tracks before you can hear it through the air, because the speed of sound is faster through the metal, right? And that sound is vibration, right? But in a quantum system, and this is something that Einstein did, is that these vibrations have to be quantized. And like we call light quanta to be photons, we call sound quanta to be phonons. And it's one of those things it's actually pretty easy to measure in modern solids. And so one of the first things people do to characterize different materials is they look at the phonon spectrum. Okay. And the phonons interact with light and they interact with other vibrations in the system. So the really clever thing that Einstein did was he realized that the idea of quantizing the vibration, if it worked for photons, it has to work for phonons, if they're what we now call phonons. And so he wrote this great paper saying, hey, if, you know, sound is quantized in solids, then at low temperatures, that would explain why the specific heat goes to zero, which is not predicted by the classical theory. And everybody went, oh,
No, it's not being like two this way, it's just different steps, is that what you're saying? It's not being just discrete steps, is that what you're saying?
yeah, kind of.
Okay.
So you know, you get like there's a little bit of vibration, and then you hit it, and it's like the vibrates in a quantized way. And you can think of these, you know, it's like a slinky, you know, it's quantized, you know, but it's quantized. It's a certain amount of energy. There's a characteristic energy scale called the divine energy that, you know, determines in a given solid, you know, what the typical energy of a phonon is once it's excited. Richard.
You compare a rate, Manhattan Project, Willis Lamb, Nobel vaccine, effort, scientific output. Words. Your writings are big.
I mean,
Our government said we need this. Massive amounts of money never put in.
yeah, well, there are different kinds of problems, okay? So, take climate change,
Why
right?
can't we?
Right, that's a big problem that faces a lot of small, relatively small technical challenges. But probably the biggest challenge we face is political, right? The landing on the moon is a big technical challenge, but in principle, it's a set of solvable steps that can, the culmination of which is risking some brave guy's life being shot up into the sky on a rocket, right? But, people understood how to do that in principle for a long time. I mean,
Engineering problem.
right, the Possum Lagrange, but it's also a political problem. I mean, we will go to the moon, and we did, right? And then we didn't go to the moon for decades after that.
But
so
with
there's
that
political
desperation,
issues.
right? War.
Right, but the Manhattan Project, the people working on the Manhattan Project saw it as an existential problem, right? Because they thought if the Nazis get nuclear weapons, we are cooked, right? And they were probably right. The Japanese were sending over balloons with bombs to the West Coast. The Germans had the V1 and the V2 technology. And if in some horrible alternate universe, the kind of nuclear technology the US and its allies developed had been developed by the Nazis, then of course it would have changed the course of history in terrible ways. So I would have to rank that as, both sort of high on the political axis in terms of direness, but also high on the technical axis as being, the solution of a lot of problems that they didn't know the answer to when they started. And you can see the indication of that by the fact that the Germans did not develop it because they got the physics wrong.
Yeah, what was the wrong term?
So the point, we know after the war, a team of people went through Europe, rounded up all the German nuclear scientists they could find and brought them to England, where they were secretly recorded and also debriefed. And they made a fundamental mistake in estimating nuclear cross sections. And with the mistake they had made, and Heisenberg was involved in the calculation, with the mistake that they had made, it looked like you could not make a portable nuclear device. It looked like you could make a very large nuclear reactor, much larger than Fermi's atomic pile 1 at the University of Chicago. And that's what they were working on. If they had succeeded in getting that device to work, I have read that there's a significant chance that they would have blown themselves up because it would have been too big. And, they thought they were going to get, sort of a low rate of fission, whereas in reality, they would have gotten a much, much higher rate of fission. And so it would have been very, very dangerous.
The majority of had the ability to make enough, the uranium 255 or whatever, because that was the other claim was how hard it was to produce the plutonium and uranium.
Mike, I'll talk about some of this next week.
Yeah, I love Lee will talk about. I know Lee certainly knows as much as I do about this era, and so it's a good thing to leave them.
May I add just one tiny bit to that? When Bohr's grandson came here, he added that one of the reasons for which the Germans did not succeed in doing that was that they could not collaborate at the American state. That they were like big personalities and they would collaborate between departments. And so they did not discover the other.
You know, some of them, some of the things like this were Nazis.
Oh, sorry.
It's certainly better than Nazi.
The big department chief of that. The Heisenberg discovery, they had collaborated.
Hang on, I'm gonna stop the, okay, hang on, I gotta,
That plot that you had of the rotational vibrational spectrum.
hang on one second. I stop video.
Yeah.